Last video for this lecture, equipotential surfaces. What important about equipotential surfaces? Let's just look at the name first and try to decipher it. Equipotential surfaces. That basically means that we're looking for surfaces in 3 dimensions where potential doesn't change. And that helps us to visualize electric field, what's actually happening. Consider this example, capacitor. One plate has positive charge, second plate has negative charge. Electric field goes from top to bottom, from plus to minus, and that also means a low potential over here, negative, and this has high potential. Equipotential surfaces are going to look like that. Here is potential 15,000 volts, here is line 10,000 volts, and here is equipotential surface represented like line 5,000 volts, and here we have 0 volts. So this is simply, again, useful way to visualize electric fields through plots of equipotential surfaces. And to say differently, this is just contours where electric potential doesn't change, stays the same. And they are in 2 dimensions. Unfortunately, we're now dealing with 2 3-dimensional world. In this example B, we see those lines shown as constant potentials. There are several rules that one needs to know dealing with equipotential surfaces. The first one is equipotential surfaces are always perpendicular to the direction of electric field. This is basically due to relationship between E and V. Now, if equipotential surface is always perpendicular to electric field line, we also can say that there is no electric field component in this direction. So, another way, for the motion parallel to equipotential surface where V is constant, this change in V is 0, there is no electric field component parallel to the surface. Let's look at the point charge. Electric field lines are going to go outwards this way if the charge is positive, so that's what we have for electric field lines. And also, if you remember, the formula for potential from a point charge is K Q over R. That means at the same distance we're going to have potentials the same. Hence, we have equipotential surfaces going like a spheres around point charge. I think kind of very logical, makes sense. And so if you look at the electric field lines, they're always perpendicular to the equipotential surfaces. That's how it is. And there is no component, there is nothing happening like that. So there is no component of electric field this way. So it's not happening. Different spheres correspond to different values of V. Let's solve problem 37. Given equipotential planes, find approximate magnitude and direction of electric field in the origin over here, and then compare it at the field at point 1,1 over here. So let's go and calculate. Make it a little bit smaller so I can write on the side, and let's go relationship between electric field lines and electric potential is given by negative delta V over delta S, where this is basically delta X, delta L, this is displacement, distance. We will look at these two lines, and so delta V is equal 10 volts minus 5 volts over distance S. What is distance? The easiest way is to look at these points. So delta S can be found from Pythagorean theorem. This is 1.5 and this is 1.5, so it's 1.5 meters squared plus 1.5 meters squared. It's approximately 2.12 meters. So you have to divide by 2.12 meters. And this is approximately equal 2.3 volts per meter. So what does it mean? That means that magnitude of electric field is 2.3 volts per meter. And as far as direction concerned, I guess the easiest way to just remember it, it goes opposite. If V gets larger, E goes away. So in this particular case, show it in show it black color. E goes this way. So at this point, E is directed this way, away from 10 toward 5. So this is answer to point 2A. Let's look at B. We can try to analyze this problem without actually calculating. Look what we have for point 1, 1. I'll use red color for this point. To use the same approach, E is equal delta V delta S. Let's go back to blue color. Delta V stays the same, 15 and 10, so it's 5. But delta S definitely gets smaller, just visually. This is way smaller. So that means this gets larger and electric field at the origin is less than electric field at point 1.1. Last problem for today, problem 38. It's a similar, it's the same picture as before, same equipotential surfaces, but now we're placing electron in a point. Which point? 1 is here and -1 over here. So that where is electron? The question is, it is from rest, what direction will it move? Well, we just found that electric field at the origin is going this way toward, and it's perpendicular to equipotential line, so it's 45-degree angle with X or Y, depends how you look at it. Electrons has a negative sign, so force on electron is going to go in opposite direction of electric field. So this is force electron going to experience. And it's a symmetrical situation. If electric field goes this way, it's going to go this way everywhere. Everywhere. Let's choose black color for force. So force is this way. So electron is going to move in on a 45-degree angle with respect to positive x axis and toward lines of higher potential. So just to summarize, so this is how it's going to go. 45-degree angle with x. This is electron, negative charge, and force going this way. Okay, that's it. We done with first part of chapter 18. We'll continue next time.